All right, so today we're going to be talking about nuts and bolts of how we actually figure out what these gradients are. A little easier to see. So yeah, lab Tuesday, Saturday. Same with the readings. Any questions on either of those? Going well? Yeah, Dane?
Is it fair to say the first few sections of the lab are basically following the video?
Yeah.
You're not looking for any innovation beyond that.
You're just learning the muscle memory of what it looks like to code a hypertrophy training. Yeah. Yeah. I don't think so. Is there anything else written in the collab notebook that you need to do? Okay, then that should be fine. Yeah. So not necessarily, but I would probably do like 30 minutes of training so you get decent good results. Okay. So last time we went over the softmax cross entropy loss function, which is also known as negative log likelihood, or what was that? Yeah, maximizing likelihood. Yep, great. So today we're going to, this is actually wrong. We're going to look at computation graphs today. And then, yeah, last time we also looked at the big picture of we get our data, we have our neural network, we come up with a loss function, and then we use gradient descent or to minimize that loss function. So today is about how do we compute the gradient. So to do that, we will start by talking about multi-layer classifiers, because in the real world, we don't have a single layer neural network. This is the deep learning class, not the linear classifier class. Then we will look at computation graphs and how we can translate a multi-layer neural network into a graph that maps out the operations that are happening. Then we will talk about the chain rule of derivatives and an algorithm called automatic differentiation, which will be implemented by PyTorch, the deep learning library that we use, but which it's very important to understand. Yeah, and so if we look at all of these different terms, and we will explain them more, PyTorch provides automatic differentiation capabilities, and it creates the computation graphs for us, which makes it easy to get gradients. And then it also offers optimization algorithms, which use those gradients to optimize neural networks. All I can say is we're lucky that we're doing deep learning in 2022. If we were doing this in 2012, this would be a lot harder. Okay, so previously we've talked about a single layer neural network where we take our input vector X, multiply it by a weight matrix W, and get scores for each class. A multi-layer neural network, we simply add a weight matrix, and that provides another layer. And if you remember, the second dimension of the first matrix has to match the first dimension of the second matrix in order for those shapes to be compatible. And you can see that here, this first matrix, if we have 3 input nodes, will be a 4x3 matrix, and then we will multiply it by a vector of size 3, and that will give us an output vector of size 4. And this second matrix will be a 2x4 matrix, where we then multiply that 2x4 matrix by a vector of length 4 to get an output of size 2. And so that's how you stack layers. Now, if you are familiar with linear algebra, this might look a little bit fishy to you. And yeah, from any guesses as to why, from a linear algebra perspective, stacking more layers in a neural network might not be the most effective thing? Yeah, back there. That's a good point. So the comment was that shouldn't you multiply them in the reverse order? And the answer is yes. So actually in this case, W2 would correspond to these synapses and W1 would correspond to these synapses. And that's a great point. Yeah. Yes, so that is the answer. So because the result of multiplying two matrices is a matrix, they're just stacking more linear layers on top of each other is no different from just having a single linear layer. And you mentioned nonlinearities. That is what we are going to add. And that is this G right here. And that makes it so that we can no longer simplify this expression by combining these two matrices, because W2, G, W1 is not an operation that can be simplified into a single matrix operation. And we can add more layers. So that nonlinearity is called an activation function. And they take various forms, but the only requirement is that it has to be nonlinear. So we'll take a look at a couple of those. So these are a couple of these nonlinearities or activation functions. So here we have the sigmoid activation function, which for x equals negative infinity to about -5, it's basically 0, and is basically 1 from 5 to infinity, and then takes meaningful values between about -5 and 5. And we have the tanh function, which is very similar to the sigmoid function in its properties, but saturates at -1 and 1 instead of 0 and 1. And we have the ReLU function, which is specified as the maximum of 0 and x, and literally just is a flat line from negative infinity to 0, and then becomes just the identity function on x from 0 to infinity. And believe it or not, that is basically the best activation function, and one of the activation functions most often used in practice, despite the fact that it is nonlinear at a single point. It is one of the best nonlinearities. Yeah, I'm seeing a couple questions.
Yeah, so ReLU essentially looks like it's just like cutting out information at some arbitrary point, right? How is that separating to?
So the question is, it looks like basically the ReLU is kind of thresholding the amount of information below a certain threshold. And the question is, how exactly does that what?
How does it make it nonlinear? How does it separate the two layers and make it so
It's because, well, I mean, mathematically, it's because you can't simplify the operation. Yeah, intuitively, you can think of it as the network learns. I think probably what it does is that it makes the learning problem pretty easy, where the network just has to learn to make values negative if it wants the network to forget them, and make them positive if it wants to remember those values. All right, yeah, question.
So ReLU is the most popular one, but one of the readings you gave us was that actually could lead to dead networks a lot of the time, and you should instead use leaky. So why aren't more people using the leaky?
Good question. So the question is, sometimes these activation functions that set things to 0 can result in dying nodes, and so people suggest not the functions like this leaky value, where instead of setting it to 0, you set it to 0.1 times x. And the answer to that is because there have been some innovations that really help get rid of that. There have been some other neural network innovations that really help with the disappearing gradients problem. And so ReLU is still used quite often in practice. Yeah.
ReLU is not continuously differentiable. I was wondering if that comes in an issue like later on when trying to optimize it.
Yeah, good question. So he's pointing out that ReLU is not continually differentiable at 0, and wondering if that comes into problem if you run into issues when training a neural network. And I believe that usually in practice, what they do is they just say that the derivative at that point is 0. You just say the derivative is the limit of the derivative from the left side, and it doesn't really make a difference because it's the measure 0 point. Okay. All right, so those are some activation functions. So didn't know that was going to happen. We can now take this neural network and translate it from math into a sort of diagram that we will call a computation graph, where we create nodes that represent inputs and outputs, as well as nodes that represent operations. So in this case, this most simple neural network where we just have f equals wx, and then the loss equals our negative log likelihood loss. We will take our inputs w and x, apply the matrix multiplication operator to those two inputs, which gives us scores. And if we wanted to, we could also make a node for scores, which then get passed into the cross entropy loss operator, which gives us our losses output. Which is kind of a fun party trick, but how is that actually useful? We're not there yet. We're going to practice making these computation graphs a couple times first. So here is a more complicated computation graph. We have the original, but now we are also summing over all of the inputs, and we also have this lambda R W term. And we've seen this before. This is a regularization term, which this regularization term is a penalty on the magnitude of the weights of the matrix W. And it helps us, generally adding regularization helps us generalize better from our trained data to unseen data. There will be a whole lecture on regularization. But that's what that is. So the question is, what is the graph for this new function? And I'm going to let you turn to the person next to you and see if you can draw this out.
So process.
That's 0 to one. First adding
So it's some value here, some non Thinking about it. Right?
Some value should be 0 and 1. Because it's 1 divided by
The sum.
whatever.
You're right.
It's the sum of.
So it's a normalized time. And then I didn't quite follow the lambda R does.
That's just taking all of our stuff.
Plus that difference.
So the question is whether lambda RW is inside the sun, the lambda RW is outside the sun.
Taking the constant, we're adding all of the things. Or is that
It's outside the log
Rand stands for
number of.
All right, so we're gonna come back together and do this.
I love indexing.
So what should be my first node in this computation graph? What are we gonna put there? We're gonna put X. What should be in my second node of the computation graph? W, all right. Okay, and someone other than Travis. What should be our next node in the computation graph? Matrix multiply, good. And then which nodes will feed into that node? X and W. Okay. What's next? I heard an activation function. Yes, you have an activation function F. Okay. Anything else in this computation graph? Yep, so then we apply cross entropy loss to that. Are we done? What is R? Yeah.
I have no idea what R is, but you should write it after cross entropy loss.
I agree. Okay, yeah, so we're going to have we're going to put it below the cross entropy loss. And W feeds into R instead. And then R is multiplied by lambda. And are we done? Need to do addition. Okay. That is a loss function. And so we could say, we can make this xi, make this loss I, and then if we want to make this the sum over all of them, we would add one more node to this computation graph, which sums all of the L-I's. Any questions on that graph? Yeah.
So just to understand like the position, you don't have a node that is a does that mean that like it's a function of the thing that the arrow is pointing to? Like R, like the arrow from W to R is the operator, but it's like R is a function of W.
Yeah, so arrows represent that the input, the origin of the arrow is the input to the operator at the end of the arrow. Yeah. Okay, yeah. You're saying are the F's different? Oh, yes. Yes. So you're wondering on the left side we have F and on the right side we have an F. I didn't write these slides, so they might be the same. There might be Yeah. Yeah, and the one on the right, we're calling an activation function. Yep. Yeah. The one over n. Yeah, so we kind of simplified and we only took in the first term of this sum, And so that would be something after what we've written on the board, where we sum up all of the LIs, and then we have n as another node, which gets, we divide the sum of all of the LIs by n. Yeah, yeah. Okay. Yeah, question? Yes, the loss function is the same cost function. Yeah. Okay.
So y sub I is the label, the output label, right? I don't know. Or
Yes,
is
y sub I is the output label.
And the j is indexing over.
Yeah, and then j is indexing over all of the classes. So yeah, we're summing over all of the classes, and this is good review from our loss function. So j sums over all of the different classes, and then yi is an integer representing a specific class. So in this case, it would be like 2, which would take the item, the index 2 item from this method. All right. And I think what we drew matches what's on the slide. So moving on, we're going to do, actually, so we have this more complicated computation graph, which we can do if you feel like you could use another practice. We're going to do a close eyes poll. Who feels like they could use, so close your eyes and then raise your hand if you want another practice at drawing a computation graph. All right, we're going to do it again. Okay. So again, we're going to, and this will be easier if you pull out a piece of paper instead of trying to do it in your head, either independently or with the person next to you. This is a computation graph taken from a paper. And here we have multiple equations broken up into multiple lines. So you'll have to figure out which of these variables depend on each other to create your full computation graph. One other comment on this, we have these superscripts t and t minus 1. You can we can assume the existence of t0 and of t equals 0. So we can assume the existence of the first nodes in the graph, and we will just predict the first R1, Z1, H bar 1, and H1.
So that makes sense, I guess.
Okay, so who still had a hard time trying to figure out how to make the computation graph for this one? Okay, I'm going to ask one of you to try to talk me through this because I think that will be the best measure of how well the class is understanding this. So what's your name in the blue baseball hat? Josh, all right. You raise your hand as not quite getting it yet. So let's work through this with you and see if we can get to a point where this makes sense. Yeah, let's start with finding R1. That's a great place to start. So what do we need to make R1? Yes, we need X1. You said U sub R. And what else did you say? H0. And W sub R. Okay. Good. That is correct. So if we have these things given, what do you want to make our first node in this graph? And I'm actually going to draw out W sub R here. And what operation between them? Matrix multiplication. Good. Okay. Then what do we want to make our next node? Yeah, same thing. All right, what next? Yep. So we'll do addition as our next operator. Oops. Undo. Okay. Okay. Yes, so we do addition between those. Unfortunately, my tip of my pen does not track very well. Hopefully that makes sense. So that gives us an output that's not yet R1, right? So what operation will we apply next? Yep. And that sigma represents the sigmoid activation function that we saw earlier. And that will give us R1. So then ZT will be basically the same thing as that, right? Except with U sub Z and W sub Z instead of U sub R and W sub R. Are we all on board with that? So we'll assume the existence of Z1. Then who is someone who still feels like they don't understand this? Josh did a great job. Little round of applause for Josh. Anyone still having a hard time with these computation graphs wants to walk through this with me? Of course.
I just have a question. So these are, all these equations, they're separate, right? I think I was trying to combine them together.
Well, yeah, so we are combining them all together.
Oh, okay.
Yeah.
Okay.
Yes, yeah. Yep, so what we said was that the computation graph for Z1 will look almost identical to the computation graph for R1. And so to avoid cluttering the slide, we're just going to assume we've got that. Yeah. Yeah, so should we start with H bar T or H2? What do you think? Yeah, H bar T because HT depends on H bar T. Okay. So yeah, and white shirt. It's a choice. In this, we could swap the subscripts and superscripts. In this case, superscript means time step, and subscript means whether it pertains to Z or pertains to R. So kind of mathematicians like to decide like how to interpret different superscripts or subscripts. Yeah.
Yeah.
Yeah, great. Okay, so what will be our input nodes? Yep. Yeah.
And I guess U and W without their subscripts.
Yes. Mm-hmm.
Does that mean like W and U are vectors? And we're just doing vectors?
No. Good. So the question is whether that means that U and W are vectors and we're not taking rows of them. R and Z do not indicate rows of W. They indicate different W matrices. One that pertains to R, one that pertains to Z, and now we have one without a subscript. So we're going to make an entirely different variable for that. Okay, yeah, so we have H0, we have U, W. What else do we need? X1, okay, we got that. Yep, and R1. Okay, so what is going to be the first, the next node of your computation graph here? Okay. So we'll do that. And I think we will probably end with H bar T because this is getting, we're running out of space on the slide. And I think we're getting there. Okay, good. What's next? No, so that is a point, a good question. So the question is whether it's a dot product. That is not a dot product. That is a matrix. That is point-wise multiplication. So multiply every entry in R with every entry in H. So yes, it's so that you maintain a vector. So I'm gonna do that one. Okay, then what? Yeah. Okay. Okay. That's correct. All right. And remind me your name. Brendan. Brendan. So those are computation graphs. So why do we need these things? And oh yeah, we skipped H, but this is the full computation graph. And they get more complicated. So this is an architecture called the neural Turing machine, and you can see that the graph gets huge. So that's why we have deep learning frameworks, and that is why we are glad that it's not 2012, because we would be doing that by hand. So the reason why we create this computation graph is because we are going to use it to compute the derivatives. So just a review on derivatives or gradients. Our neural networks are functions from Rn to R, and the gradient of the loss is the vector of partial derivatives. And when we specify gradient, we say the gradient of x with respect to y, where x is the output in R, and y is the inputs in Rn. So the derivative of the loss with respect to the weights of the neural network. So that gives us this vector here. Then we can use the gradient descent algorithm to update our weights with the learning rate times the gradient of the loss with respect to that individual weight. And intuitively, that does the following. It says, which direction do we need to tweak the weights so that the loss goes down? So we follow this loop until we minimize our loss function. How do we do it? Calculus. So if you think all the way back to Calc 1, this expression on the right here may look familiar. The derivative of f of x with respect to x is the limit as h goes to 0 of f of x plus h minus f of x over h. And that basically is just saying how much does our function increase over a step of size h. And so we're going to do that here. So our current w is 0.34. We add a small step size h, and we then evaluate the function at that point, which is, so we take this first number, 1.25322 is f of 0.34. The second number, 1.25347, is f of 0.3401. And that gives us basically the difference in height, the change in height, divided by the step size, gives us the slope of the loss function at that weight. Any questions on that? Yeah. So the question is whether this is the loss of the first dimensions of the vector, or all of the inputs. And the answer is it is all of the inputs, because yeah, the loss is a function of all of the weights. But we're only changing the first two. Okay. Then we do that in the second dimension. And the third, and so on until we get the full gradient vector, which we then multiply each of these numbers by the learning rate and add to our current w to get the new w. So negative 0.25 times 0.1 is negative 0.25 plus 0.34 equals 0.09. Yeah, question.
What's the difference between step size and the same? You in the last slide.
They're not the same. So yeah, in the previous slide, good question. So in the previous slide, the step size had to do with our approximation of the gradient. Whereas in this slide, the step size has to do with the size of the step that we're taking in the direction of that gradient. So to reiterate that another way, in this slide, how small h is determines how accurate our gradient is. If h is tiny, then our gradient will be very accurate. Whereas in this slide, h determines how fast our network moves based on that gradient information. Yeah. How we got h? We just chose it. Yeah, that's just we tried to choose a sufficiently small number that it would give an accurate read of the gradient at that spot. So the idea is that hopefully the curvature of the loss surface is not changing very much in a radius of 0.0001 around that way. Yeah. So yeah, the question is this how it is done in practice rather than computing the exact derivative? And the answer is no. We do compute the exact derivative using full trick. So good question. Yeah, Matthew.
I was going to say, just to kind of contextualize the code, and for what you just said, maybe this is wrong, but the computing of this part where the computing of the derivative, that's the loss backward function. And in the next step, so thinking about calculating the step size and calculating the change of the weights, that's what the optimizer does.
Yeah, that's optimizer.step. That's a great point. Yeah. So what Matthew just said, to reiterate, is this first step where we calculate the gradient is loss.backwards. And then this next step where we update the weights is optimizer.step. Thank you. So what's the problem with this? Can anyone see any problems with this mode of computing the derivative? Yeah. Yeah, so you're pointing out that we're not taking into account any of the hidden layers of the neural network, which is kind of true. But they are taken into account implicitly because we use them to get the change in loss, right? It's a good thought, though. Yeah, Michael.
It's erroneous and computationally expensive.
Yeah, it is extremely computationally expensive. We're going to have to do this for every single weight of the neural network. Yeah, question. Yeah, you're right. It's also definitely potentially numerically unstable. And we're also you pointed out that yeah, this is also an approximation to the gradient. It's not the true gradient. So there's a better way, and we're running out of time. But yeah, we should probably leave off here. But the chain rule of derivatives is a magical thing, and it's going to allow us to do much faster differentiation, which we will call automatic differentiation. So we look forward to that.